name is Evgeny Epifanovsky. I'm a staff scientist at QChem, and I will be the moderator of today's webinar. So today's webinar speaker is Adrian Morrison. Adrian is working at Ohio State University in John Herbert's group, and his topic of research is methods for excited states, and that's what he's going to talk about today. Please welcome Adrian Morrison.
All right, so thanks again. I'd like to talk about some new methods for excited states in QChem based on an ExTown model. So to motivate these methods, there are two classes of problems that we're interested in. And for both of these, we're going to consider a system that would be an aggregate of weakly interacting molecular fragments. So the first type of excited state where they're interested in studying is a coherent delocalized excitation. So where our excited state is spread over multiple chromophores in this aggregate. So for instance, we have the Fenner-Matthews-Olsen complex. This is a set of chromophores in green sulfur bacteria. It's involved in the electron transport chain. And there is an open question about the role that quantum coherence plays in the energy transfer mechanism. Now, pictured here are the 8 bacteria chlorophyll chromophores in the main reaction center. And these are typically treated for simulations of the system. But really, there's more going on here. The full Fenner-Matthews-Olsen complex is a trimer of these sets of chromophores. And recently, there have been some semi-empirical studies that have shown that considering the full trimer of the system changes the characteristics of the energy transfer. For instance, the black lines in this plot show that population transfer occurs from actually the often ignored 8th bacteriophile chromophore between these monomer subunits. And that by considering the full trimer, it really changes the picture of the mechanism. Obviously, this is too large for traditional quantum chemistry methods, but we want to be able to tackle things like this. We're also interested in organic semiconductors. This is a self-assembling nanotube structure formed from naphthalene diamide subunits. This was characterized by some collaborators of ours, and we did some TDDFT calculations in our group in order to get a picture of the energy transport mechanism within the system. It's a sub-picosecond transfer time. This is actually a pretty challenging calculation to do with traditional TDDFT, and that's because this is in a 9-monomer model system here, and that's because the bright state that we're interested in is actually about the 30th excited state root. This incurs a significant memory bottleneck for typical TDDFT, and we did these calculations with the somewhat disappointing 321G star basis set. By our estimates, increasing to something like 631G star would add on about 30 gigs of RAM requirement. And while that's available for plenty of systems these days, the principle of the problem remains. We're also interested in extended systems around a chromophore, excited states where the environmental effects are important, such as computing the solvochromatic shift of various chromophores. For example, this is the trans-thiophenyl P coumarate molecule. This is a model chromophore from yellow fluorescent proteins, and has been shown to exhibit a significant blue shifting in aqueous solution of up to 25 wave numbers. We would like to be able to simulate this sort of thing, and really take the solvent, the explicit solvent system, out to considerable sizes to really converge these excitations. So the overarching theme here is that these are rather sizable systems by traditional quantum chemistry standards. We want algorithms to be able to handle these sorts of problems with reasonable computational cost. So our approach to these things is based on an exciton model, and this is a pretty old idea where the excited state of some aggregate weakly interacting chromophores is approximated as a linear combination of excitations localized on molecular sites. So for instance, this tetracene dimer excited state is some linear superposition of excitations that are localized on either of the two monomers. You can write the wave function for such a state as a direct product of fragment wave functions, where in each term, one fragment is in an excited state and the rest are in their ground state. we solve for these K coefficients simply by computing the matrix elements of the electronic Hamiltonian in this so-called exciton-site basis, and we just diagonalize it. So there are two methods based on this approximation or on this model that I would like to talk about today. The first is called the Ab-Initio Frenkel Davydov exciton model, or AIFDEM, and the second is TDDFT for molecular interactions, or TDDFTMI. We'll start with the Ab-Initio Frenkel Davydov exciton model, and we can outline the algorithm here, break it down into 5 steps. To start, we do ground and excited state calculations on the isolated fragments. The fragment definition is up to the user, although we are not supposed to break covalent bonds. We found it helpful sometimes to include polarization effects explicitly in the ground state calculations through a self-consistent charge embedding procedure called XPOL. The excited state calculations then use these polarized MOs. We also transform the fragment excited states to the natural transition orbital basis. And this is the most compact representation of singly substituted wave functions. We'll see why this is important on the next slide here. With the fragment orbitals, we can construct our exciton-site basis states. And as dictated by an exciton model, these look like direct product states. So for instance, the ground state looks like a direct product of fragment ground state SCF determinants. The excited states then look like a direct product of fragment configuration state functions, where the T coefficients come from the fragment excited state calculations. Here we will introduce probably the most important parameter for the method, and this is the threshold of the excited state amplitudes with which to include in these summations. See, for cost savings, we can truncate these. They're already fairly short thanks to the natural transition orbital basis, but we can truncate them further. And usually the higher this parameter is turned up, the more the calculation will cost, the more accurate it is. Approximately quadratic with the number of NTOs. For organic chromophores, around 85% we found to be a good balance of cost and accuracy. And I'll be going over these keywords again later. Might also include charge transfer-like configurations if our problem requires it, and these are simply constructed from unrestricted SCF determinants. There's another keyword for that. Most important step is the matrix element evaluation, and I'm going to gloss over this theory kind of quickly, but you can go through it again in our publications. But we need elements of the overlap and electronic Hamiltonian matrices in the exciton-site basis. For this, we use a technique called the corresponding orbitals transformation, which diagonalizes the MO overlap matrix via singular value decomposition. And we use generalized rules for matrix elements to get fairly compact expressions for the elements that we need. There's one key point here, and that is because we are including exact Hartree-Fock exchange interactions, this unfortunately causes the method to scale with the size of the supersystem, since these interactions are non-local. All of the fragments must be included in this direct product basis, and this is obviously not ideal for a fragment method. The exponent shown for the scaling, the 2 to 4, represents the scaling of the 2 electron integrals. Thankfully for QChem, they're quite efficient. Formally, it's 4th order scaling, but thanks to integral screening, this can go down to quadratic depending on the system, the nature of the system. But we can get around this supersystem scaling with a charge embedding scheme. And this is based, or it's inspired really, by QM-MM approaches, where we can partition our system into a significant region that contains the 2 excited fragments, and we treat the significant region with full QM, as in the previous slides, but we approximate the rest of the system with point charges. Here we introduce another parameter, and this allows users, or allows one to introduce a range to adjust the size of the QM region with some threshold range, where we include nearby fragments to those that are excited, and this is also controlled via an adjustable parameter. Once the matrix elements have been evaluated, we can simply solve the generalized eigenvalue problem, and diagonalize the Hamiltonian. And so we have a well-defined LCAO wave function. All of the properties that are available in QChem are available to us. Simply evaluate the operators in the exciton-site basis, which allows us to get something like a transition dipole moment, as shown here. We also have a chemically meaningful representation inherent in the exciton-site basis. This basis is a non-ambiguous diabatic representation of localized excited states. This is useful for analyzing excited state properties. For instance, we've used this sort of thing for exciton dynamics in our group with red field theory, and the operators that you need are saved to the scratch directory. So let's look at some results. These pictures are the natural transition orbitals of a supersystem CI singles calculations. This is a traditional calculation we're looking at. And from the NTOs, we can see that this excitation is composed primarily of two localized excitations, primarily located on fragment 1 with 76% of the amplitude, and also on fragment 3, the smaller amount of the amplitude. We did the same calculation with the AIFDEM. We can examine the eigenvector, look at the coefficients, and see that the most significant coefficients correspond to the same two fragments, indicating that qualitatively we're tracking the same state. You might notice that the relative amplitudes, however, of these coefficients are reversed. And we can explain that because the polarization effects that are important for systems like water are missing from the isolated fragment calculations. We can capture those implicitly, however, by expanding our exciton-site basis to include higher-lying excitations. This will increase the variational flexibility of the basis. We include 3 excited states per fragment. We keep the same correspondence to the supersystem calculation, but the relative magnitudes now also match. If we look at some quantitative results here, so these are excitation energy errors relative to the supersystem calculation for a series of water clusters of different sizes, 2 different AO basis sets, and errors are not awesome, but we can tell that they are consistent, and we're tracking the states that we're interested in. But again, water is polar, and we need to somehow capture those polarization effects, and we can do that by expanding the basis. So by including 3 excited states per fragment, we reduce our error significantly to be in the order of a couple hundred millieV. We can do one better by explicitly capturing the polarization effects in water with XPOL, and we get excellent agreement with the supersystem results. These data have also utilized our charge embedding procedure. As you can see, it maintains very good accuracy. Can further examine the charge embedding procedure here. Now we're looking at larger systems. These are snapshots from liquid water simulations, and the blue data use the minimal QM region where only the 2 excited fragments are treated with QM, and the purple data have an expanded QM region with a 3 angstrom threshold. We're also looking at different charge schemes and AO basis sets here. And other than the expected failure of Mulliken charges to perform well with extended basis sets, most of these results look quite good. Agreement on the order of 100 or so millieV. What's also interesting is that the minimal QM region seems to be sufficient. The results are just as good as the expanded QM region, so we think that it's sufficient for acceptable accuracy. And it's also significantly cheaper, as even a 3 angstrom threshold requires a significant number of fragments to be treated with QM. We can look at some organic chromophores of clusters of dimers and tetramers of organic chromophores. These, again, are excitation energy errors relative to supersystem. We have naphthalene diamide, which is the building block of that nanotube from earlier, tetracene, which is important in the context of singlet fission, and guanine-cytosine base pairs. Now, the horizontal lines here are the results without charge embedding, and the vertical bars use our charge embedding scheme with the minimal QM region again. And all of these results agree quite well with supersystem calculations errors of about 100 or so millieV. talk about scaling now. Thanks to this charge embedding scheme, the cost of the method scales quadratically with the number of fragments and only polynomially with the size of a pair of fragments at most. However, the matrix element evaluations, which are the bottleneck tasks of this procedure, are entirely independent of one another. Therefore, if we have enough processors, the time to solution can scale merely as the size of a pair of fragments. That we're able to achieve speedups of up to 200 times faster than the supersystem calculation. Now, these matrix element evaluations are distributed with MPI parallelism, but if we have, for instance, if you have a lot more cores than you have matrix elements to evaluate, so if you have a smaller system, OpenMP parallelism is a better choice, and it will distribute the two-electron integrals in the usual way. With this excellent scalability, we managed to push this method to some pretty large size regimes. This is some varying sizes of that nanotube system, and we've been able to run calculations on the equivalent of about 50,000 basis functions with hardware that one might have in a laboratory cluster. Here's a brief rundown of job control for the AIFDEM. We use the fragment QChem input, standard QChem fragment input section on the top there, shared by other fragment methods. And again, we're not supposed to break covalent bonds. Now, the exchange functional specified in the input only indicates the functional to use to compute the fragment orbitals. Essentially, the Hartree-Fock functional is always used for the matrix element evaluations. The sys and roots keyword in red specifies the number of excited states to include per fragment. If we want to expand our variational flexibility, we can increase that. We must specifically indicate the multiplicity of the target state with the keywords that are in blue, cis singlets and cis triplets, since the exciton-site basis is spin adapted. The NTO threshold keyword in green is again used to adjust the number of terms retained in the exciton-site basis state expansions. The higher this is, the more accurate the results are, but it does increase the cost. Again, around 85, we found to achieve a good balance. The embed range keyword in orange will invoke charge embedding. If this keyword is absent, no embedding is used. 0 for this keyword will specify the minimal QM region, and this can be adjusted for users to try playing with this QM region. The purple expo keywords at the bottom are optional and can be included to get some approximate polarization effects in the ground state for the fragment calculations. All right, so in summary, the AIFDEM is a ground-up implementation, Ab-Initio implementation of an exciton model. Currently, it can be considered uncorrelated. The matrix element evaluations use the Hartree-Fock functional. This is something we are currently pursuing in our group. But we do see excitation energies within about 1 to 200 millieV of supersystem calculations. With MPI, we have perfect parallel scaling that lets us treat some truly huge systems, and parallelism is available for smaller calculations. Also, the localized exciton-site basis gives us some really interesting insight used towards exciton dynamic simulations, and we've just recently derived analytic gradients, and those will be available in the not-too-distant future. All right, so now I'd like to talk about TDDFT for molecular interactions, or TDDFTMI. And this is not my work. This is developed by a postdoc who was in our group, Dr. Zhu Liu, who's now working with Professor Walter Thiel. And rather than a ground-up realization of an exciton model, this is rather a top-down excitonic approximations applied to traditional linear response TDDFT. And in our group, and we have found that this method is particularly well suited for localized excitations in some sort of extended environment. We can break this algorithm down into 4 steps. So first is to converge the SCFMI, and this is where the method, this is the namesake of this method, SEFMI was invented by Stoll back in the 80s and was more recently implemented in QChem by the Head-Gordon group. And this is a fragment method. Again, we partition our system into fragments, but we also partition the Fock matrix into a series of blocks, each associated with the fragment. And the orbital solutions for those Fock matrix blocks are restricted to occupy AOs on the corresponding fragment. These are called absolutely localized molecular orbitals. They are only orthogonal within a fragment and are non-orthogonal among different fragments. With these ALMOs, we perform TDDFT on the subsystems, limiting the excitations for each subsystem to only involve the ALMOs from the given fragment. And again, since they are non-orthogonal, we need a non-orthogonal version of the Cassida equation, and it looks a lot like the orthogonal version. We pick up a few factors of the overlap matrix down on the bottom. The local excitation approximation is really the exciton part of this theory. We approximate the density response of the system as a linear combination of response terms originating from different fragments. The U coefficients in this equation are analogous to the K coefficients that we saw in the AIFTEM. We can use the fragment transition density matrices to compute coupling elements, and we will diagonalize this expression to find our U coefficients and excitation energies. Now, if we're interested only in a localized excitations, we simply limit the M and N indices here. We only allow the excitations to occur on a particular active fragment. There's one more trick that we use to reduce the cost. The coupling elements actually involve these delocalized occupied orbitals here in this tilde representation, but we will project these onto only the AOs that are on the two fragments that we're trying to couple by minimizing this functional D. Essentially, we're minimizing the difference between the original orbitals and this projected representation. And this is accomplished by solving a set of linear equations in the bottom line. So we can look at some results. Here's our nanotube again that we know and love. We're looking at 4, 6, and 9 monomer models, and we see excellent agreement with the supersystem calculations for the first triplet, first singlet, and as well as that approximately 30th highest state. That's the bright state. Errors in the order of about 100 or so millieV. Also, excellent performance relevant to full TDDFT, shown in the panel on the right. You can look at a localized excitation in an extended explicit solvent environment. This is aqueous acetone, a number of different configurations with a few different AO basis sets. See almost perfect agreement with full TDDFT, about an order of magnitude faster. And we can use, the efficiency of TDDFTMI will facilitate the computation of solvatochromatic shifts. Since here we've computed many different excitation energies from a number of different configurations from MD simulations in order to compute the spectral shifts. The LEAQ results here in red. It's a particular flavor of the local excitation approximation. More details are given in our publications. Finally, a fortuitous bonus of the of TDDFTMI is that due to the fact that excitations are limited to only the MOs involved, the MOs for an active fragment, the spurious charge transfer excitations that are common in TDDFT due to the self-interaction problem are excluded by construction. Therefore, for full TDDFT, we see this artificial lowering of the excitation energy due to these spurious charge transfer excitations, and those are non-physical, and they're immediately excluded from the TDDFTMI results, which quickly converge to a physical result. So Here's the job control for TDDFTMI. It's pretty familiar if you've done TDDFT in QChem before. Again, we have the standard fragment input section. Although notice that one of these fragments is different, and this is going to be our active fragment. Otherwise, this is pretty familiar. The functional is, we can use any functional in this case, I believe, and we've tested a number. The keyword in green is the flavor of the local excitation approximation. Again, there are a few of these. The details differ slightly. For a localized excitation, we can also specify an active fragment. 0 here refers to the first one in the list, which is the acetone. If this is absent, we do a full delocalized excitation. All right, so in summary, TDDFTMI, it's top-down excitonic approximations applied to linear response, TDDFT. And this is compatible with the full suite of functionals in QChem. Excitation energies are from about 100 to or a few hundred millieV of supersystem calculations, and standard OpenMP parallelism is available. We found this method to be well suited to localized excitations within extended systems such as explicit solvent effects, which are essentially included for free since they do not participate in the excitation. All right, so I'd like to make some acknowledgements. My boss, Dr. John Herbert on the left, me in the middle, Dr. Ji Liu on the right, who did the work on TDDFTMI. Of course, I want to thank QChem for being a fantastic piece of software, fantastic group of people, Ohio State University, and the Ohio Supercomputer Center for computer time, as well as DOE and the NSF for funding. All right, I'd be happy to take your questions. Thank you.
Thank you, Adrian. Going back to AFDM, the water cluster that you showed and with localized excitations, where each of them were localized in the water molecule. So how do you identify different states when your molecules are all the same? Because how do you distinguish between the states?
So each exciton-site basis state corresponds to a localized excitation on a molecular fragment, and they are distinct as given in the input file. Each coefficient corresponds to one of these basis states that corresponds to a specific excited fragment. Does that answer the question?
So essentially, the fragments are not identical; they are distinguishable.
Right. They're all distinct.
Okay. Second question is in AFDM. How do you extend it to the TDDFT, and namely, how do you compute the exchange correlation contribution to the coupling matrix?
Right, good question. So that's honestly something we are currently working on. At the moment, the AFDEM coupling elements uses the Hartree-Fock Hamiltonian. So it's the exact Hamiltonian, but there's no TDDFT exchange correlation at the moment, and that is fundamentally limited by the corresponding orbitals algorithm. This is something we're working on. You can use TDDFT on the fragments to get your orbitals. You can use Confam orbitals to play with, and this is something we've looked at. But at the moment, there's no TDDFT exchange correlation in the couplings and the matrix element evaluations.
Okay, and then the second question about AFDM is how to ensure continuous potential energy surface with the cutoffs.
For a non-zero cutoff, it probably would not be continuous. And in that case, I would recommend either no charge embedding or using a minimal QM region, which works pretty well.
Another question is, what are the limitations for these methods? So the range of applicability for both of them.
Sure. Well, I think fundamentally we need aggregates. If you're looking at some big protein or something that's not the right type of system for this, anything with strong correlation will also cause a problem. Want a good idea of qualitatively of how the excited state looks. I think these will work pretty well.
And what about the character of states?
Character of
excited states. So does it only is it only applicable to localized states?
Well, the AIFTEM can treat delocalized excited states pretty well, since we can have any sorts of linear combinations of different basis states.
Thanks.
And again as well.
Okay, and then one last question. Can we compute HOMO and LUMO in TDDFT? I think the answer is yes. And what about electron density? HOMO and LUMO with TDDFT. Oh, sorry, HOMO LUMO with DFT.
So with TDDFTMI, yes, definitely.
And then what about electron density and average localization?
For TDDFTMI, yes. The total density looks like a sum of the subsystem densities.
Thanks, Adrian, for answering all the questions and this great presentation.
This concludes our webinar. We would like to thank Adrian Morrison for his excellent presentation, as well as Shunting Gan or Evgeny Epifanovsky for organizing, moderating, and running this webinar. Should you have any questions, please feel free to contact us by emailing either Shunting or Evgeny at the email noted on your screen. We also invite you to visit us on Facebook. Thank you for your participation, and see you at the next webinar.